So let's see. Okay, here's a problem. You are given a series like this one. Okay. My question is how many methods you can use to prove the version of version. Okay. So I want you to think about first. I'll give you half a minute. Is the instant positive? I think it is, right? This is n, right? I think this is positive because 1 of n is very small, then sign of 1 of n is positive number. So question is it convergent or it is divergent and why? How many tests we can use for series, for test this convergence of series? Well, instant test for divergence, comparison test or limited comparison test, ratio test, integral test, Rota test, right? Integral test then have to evaluate the integral. And you have to also have to prove that this is going to be decreasing function, okay? A decreasing sequence, right? Sequence is decreasing. By the simple observation, I see that this is going to be 1 of n divided by 1 of n. So this two same. So actually the limit is going to be 1 as n approaches infinity. So clearly the limit of n is not going to be 0. So therefore the series is divergent. Okay, by the nth term test. Okay, so that is the simplest. Okay, I don't think you can use a ratio test and Rota test to solve this problem. Okay, integral test is still difficult. You know, you have to show that n is decreasing. Actually, maybe not. Okay, so this probably is the only method you can use. And how about this one? Okay, how many different ways you can solve the problem? Okay, I think this is going to be convergent. Okay, because the numerator is a polynomial. Denominator is power function, so the ratio. Now the numerator can be ignored. Okay, so you can solve this problem using I think I'm going to use this. Yeah, there are many ways to solve the problem, right? Use a comparison test. So an is going to be n squared plus 1 5 to the n. Or you can use this comparison or limited comparison test. Now, if you use a limited comparison test, your Bn cannot be 1 over 5 to n because there's an n squared there. Okay, so this you have to really be smart to get to find the Bn. I'm going to use Bn like a 1 over 4 to n. Okay, then the limit n over Bn is going to be n squared plus 1 by 5 to the n, and here is going to be 1. and the limit is going to be 0. Okay, the reason is here's n squared plus 1. And this is a you can say 5 over 4. The reason I want to choose 4, which is less than 5, because I want to make the denominator as large as possible, grows fast. Okay, so the base here is 5 over 4 is greater than 1. So you can use a Rupee to the limit is 0. Okay? So if the limit is 0, okay, then according to the limit comparison test, okay, so 0 is less than 1. That's all we need. Okay, and since this is convergent, okay, this is a convergent. This is convergent. This is geometric series. Okay, includes that implies this is a convergent. Okay. Okay. The limit comparison test essentially is a comparison test because if the limit n over Bn is 0, n over Bn is going to be less than or equal to 1/2 for large n, right? We don't know what capital N. So in other words, n is equal to half of Bn. So use that, and this is 1/2. Here's a quarter to the nth power. So that is magic. So that's why you can apply the comparison test. Okay. So essentially, you know, you compare n with another, another convergent geometric series. All right, this is a limited comparison test, but you have to be really, you know, be smart somehow. You know, based on my experience, I choose 4. You can choose 3, you can choose 2, but you cannot choose 5. Okay, if you choose 5, the limit will be infinity. It's useless. Okay. Another way to solve the problem use a ratio test. Okay. So the ratio test here is n plus 1 square plus 1, 5 to the n plus 1. And turn upside down, 5 to n square plus 1. Okay. So simplified. And this will be 1 over 5. Okay. Right? And now this term approaches 1. So it approaches 1 to the 1 over 5. That's 1 over 5. Okay. This is the L. L is less than 1. Then you can see that. Okay. Then you can conclude that n start from 1 to infinity is convergent by the ratio test. Okay. All right, so by the ratio test, and then you solve the problem. Now, usually, okay, you can also use the Rota test if it does not contain bacteria. Okay, usually you can use a Rota test. Okay, if it does not contain bacteria, that's possible, right? And so this is convergent. Let's go. Let's try to use a Rota test, right? N is going to be n squared plus 1 over 5 to the n. So to use a Rota test, can also combine it with a ratio, with a comparison test. Maybe a little bit easier because otherwise there's +1 here, right? You know, you can say it's less than or equal to n squared over 5n, right? This is Bn, but how do you prove Bn is convergent, right? Then you can say, okay, nth root is going to be nth root, right? Okay. So that is going to be nth root to n square and 5. So the limit is 1 to 5. Right? All right, so that means this implies this series is convergent. Right? And this is convergent because by the Rota test. Okay. Then you because this is this inequality, then this implies this is a convergent, okay, because it's finite. Okay. This is true only when n is a positive, because you either it's finite or infinity. There's only two options here, two possibilities here. Okay, two possibilities, not two options, two possibilities. Now, because n is less than or equal to Bn, so and the series of Bn is convergent, it's finite. That implies the series of n is convergent. So this is by the comparison test. Okay. Now, if you want to do directly without using Bn, that is okay. The question is, are you able to figure out the limit of the numerator? Okay. The limit. Okay. So that's a question, right? The limit of the numerator is going to be 1. Can you see that? So I can, yeah, it's not a trivial, okay? I can take n squared out, and this one, then it's going to be n squared to the n, right? Then n's power 1 plus 1 of n squared. This is going to be so this approach is 1. How about this part? This approach is also 1. Okay. And how do I know? Is there any quick way I can see why the approach is 1? You have to prove that. That's why it's difficult, right? I can do this way. This side is always going to be this, right? It's going to be 1, right? No problem. So the upper bound, and this is less than 1, so it's 1 plus 1. How about that? That's a 2 to the 1 of n, right? So this term is between 1 and a 2 to the 1 of n, but this approaches 2 to the 0. 2 to the 0, this is always equal to approaches 0, right? It's 1. So that's why by the squeeze theorem, the one in the middle approaches 1, right? Okay, so that implies 1 plus 1 of n squared equals 1. Okay, so we conclude this. Then I find out the limit of this term is going to be 1 over 5, which is less than 1. And then you still can show the series is convergent. So that implies this series is convergent. Okay, convergent by the Rota test. Okay, got it? So easy method, there is a difficult part here. You not probably you are not able to get 4 credits. Like you use a Rota Test, apply the Rota Test to the series directly. You have to prove that this limit is going to be 1. Okay, you just cannot claim it's 1. You have to give an argument. Here's the argument. And it's between 1 and 2 to the 1 of n, and that is a difficult part. Right? Then you can show that this limit is 1 over 5, which is the same. Okay. All right, let me ask you to do the next problem. This is also from the book, and this is e to the 1 of n and n squared. Right? So, questions. Yeah, how many methods can you use to prove it is convergent or divergent? First one, e to the 1 of n. E to the 1 of n. How does it look? E to the 1 of n. Yeah, make observation first. E to the 1 of n approaches e to 0, which is 1. So the numerator is almost equal 1. That's great. Right? The numerator is almost equal to 1. So this is my n. So the series is almost like 1 of n squared, right? So I'm going to denote by Bn. So now you can use a ratio, use a limited comparison test. And you compare with the Bn. So that is going to be, they all canceled out, just 1 of n left, which is 1. So by the limited comparison test, the convergence of n, sigma n, and the convergence of sigma Bn are the same. So since we also know that this is going to be convergent. Okay, this is convergent because the P series test by the P series test. Okay, so that implies because n is almost like Bn, right? For a large n, so that's why it implies this one is convergent by the limited comparison test. Okay, so limited comparison test is the best way to solve the problem. Now, if you don't want to use a limited comparison test, that's fine. Okay, your n is going to be e to the 1 of n divided by n squared. But e to the 1 of n is going to be e to the 1. Less than equal to e to the 1 because the 1 of n is less than equal to 1, right? So that's enough. That's good. So that's my Bn. And the Bn is just constant times 1 over n squared. So Bn is convergent, right? So this one, okay, because the e to the 1 over n squared, it's a finite. This is by the P series test. So essentially it's a limited comparison test. It's the same, right? So that implies, because this side is positive, so that implies this limit is finite, okay? And by the comparison test. Can you use an integral test? Well, technically, yes, you can. It's almost impossible to do that, to evaluate integral. Can you use the Rota test? It's a ratio test. I think neither of them works. Okay, so I should say that note the limit of n plus n is 1. So you cannot use a load test. The limit of the nth root of n is also equal 1. So we cannot use a ratio test and root test here. Okay. All right, so let me ask you to work on this problem. Check this. N factorial to the nth power, wow, n to the 4th power. Okay. Yeah, what is the best way to solve this problem? Okay. Let's see. So you see n factorial. You also see the exponential function, right? And so I think I should try to use the ratio test. But if I use a ratio test, then I have this nth power here. So this is my n, right? It's very complicated if I change n to the n plus 1. So I'm going to use the Rota test first. Usually I don't want to use Rota test when I see n factorial, but this is a special time. Okay. This series is so special because there's power n there. Okay. Then you get n factorial here. You don't need to look at the nth root of n factorial. And it will be n's 4n divided by n is 4. And clearly this approaches infinity as n approaches infinity because n factorial grows much faster than n to the fourth power. Why? Why? Well, you can see that, here's 1 times 2 times 3 times 4, 5, right? And the 6, there's so many here. Then you only have n, right? And you can put n here. So put this way. Yeah, let me write down more details here. I just want to explain to you why this is going to be. Yeah, 1 times 2 times 4 all the way to here is n minus 1, n minus 2, n minus 3. Here n minus 4. This n, because n to the fourth power. Now this part approaches what? No problem. But how about this part? This is n minus 4 factorial. Clearly this approaches infinity. So infinity times 1 is infinity, right? Okay, that is a reason. So I can tell. And this is the infinity greater than 1. Therefore, the series is divergent, right, by the Rota test. Okay. Right. Now, then you use a compression test directive. Well, actually, you can do that easily. So an is going to be n factorial. I can also use a ratio as a. I can also use the nth Rota test. Right. The question is, you want to make sure this is greater than or equal to 1. Right. Right. So just for the same idea, here this is n factorial, n to the fourth power, right? As long as this number is larger than 1, then this an approaches infinity. So that is going to be 1 times 2 times 3, n minus 4, right? Then n minus 3, n minus 2, n minus 1, n divided by n, right? To n's power. Now, I said that this number is always, this number approaches 1, right? This number approaches infinity. So the product would be greater than equal to 2 for some larger n. So you can, yeah, you can, I guarantee the product approaches infinity. That's why this part should be greater than n, greater than 2. So then greater than 2n, okay? Why this is greater than 2? Now, for what n? N can be, I think n can be, it's not easy to say, but I know the limit is going to be infinity. So that's for some large n. Okay. I don't need to know the exact number. N could be 100, capital N. Okay. So that's why this is going to be greater than 2 to the n for larger n. So that's why the limit of the nth term is greater than, is going to be infinity, right? So this is infinity, therefore the series is divergent by the nth Rota test. Right? those are the two methods, think about. All right, so here, next problem. This is a problem number 34, I think. N plus n cosine square n. Yeah, please think about this problem and to see whether it's convergent or divergent and prove it. Right. Okay. We'll figure out how to do this problem. All right, so first of all, you see cosine square n there, right? But cosine square is between between 1 and 0, right? That's it. So there's not much change in the denominator. So denominator almost like an n, right? Right, the maximum possible value for the denominator is going to be n plus n, which is 2n. It's between n and 2n. So I think it's going to be divergent, okay? And then if you put in the denominator, this is going to be less than 1 over n, greater than 1 over 2. And we know that, okay, it's by comparison test, right? What I need is just this part. That's all I need, because you want to prove that this is divergent. Okay, so this side is infinity. Okay, this is by the P series test. P1. Okay. Okay. So the left-hand side is infinity, then the right-hand side is of course infinity, right? So that implies this is going to be divergent. Okay, and by the comparison test. Okay, this probably should be the direct simplest way. You cannot use a ratio test. You cannot use a Rota test to solve this problem. Okay, they're not a universal test you can use. Okay. You even cannot use a limited comparison test. Okay, we cannot even use a limited comparison test. Clear. Okay, so Bn equals 1 over n, right? Then look at the n over Bn. N over Bn is n plus n n over 1, right? And after you simplify, you will get 1 plus cosine squared. And this one, the limit doesn't exist. So I know, yes, the limit does not exist. Although I know that, and although I know that n over Bn is less than equal to 1, greater than equal to 1/2, but it does not approach any fixed number. But so that's why this is why you cannot use a limited comparison test. So we cannot use a limited comparison test here. Okay. So now let's take a look at a very strange number. Nature log n to the power nature log n. Okay. So there's two nature log here. What do you think? Do you think it's convergent or do you think it's divergent? Okay, what method are you going to use? Okay. All right, so you cannot use clearly this nth term approach is 0. Okay, right? The new denominator is getting larger and larger. You cannot use integral test. You cannot use a comparison test directly. Yeah, nth Rota test does not work. Okay. The only possible way you can try to prove this is going to use a comparison test. Okay, so here's my trick. I want to prove that for n sufficient large n, natural log of n is greater than e squared. Yeah, you'd be surprised, yeah. So that is true when n is very large, okay? This is equivalent to say n is greater than equal to e to the e squared. Okay. So anyway, this is some number. Could be one, what is that number? Well, you can make it easy. E squared is less than equal to, E is less than 3, right? So E is 3 squared, so E to the 9. So it's less than 3 to the 9th power. Okay. E to the 3 to the 9th power is some big number. Okay. Do we need to care about that? Well, I can find out the number, just use my calculator. Okay. Use my calculator. Okay. So let's see. I need to punch 9 times, right? So let's say, so this is number 19683. Okay, great. So that is, yeah, so natural log of n is greater than e squared if n is greater than equal to, 19,683. Okay, then let's see, natural log of n, you will know why I have to put square there. So natural log, okay, is greater than or equal to e squared, right? Okay. And then e to the 2 times natural log, right? N. And that is going to be e to the natural log of n squared, right? And that is nothing but n squared. So what I did is that I tried to prove this one is greater than n squared for n greater than 19,683. Okay, now it's put in the denominator. And that's my Bn. So I find the Bn I can compare. This is a convergent, you get a convergent series. Okay. So since n from some capital N, right? This is my capital N, this Bn is convergent. This is by the P series test. Okay. Then I conclude that, and this even can start from 1, okay? And is finite because you don't need to know field first. Yeah, the the first few terms does not change the convergence. So it's by the comparison test. I think the difficult part is to figure out which series you're going to compare with. Okay, when I look at natural log of n to the natural log of n, I know it grows faster than the, it's kind of exponential, but it's natural log. Okay. This probably is the only way, you can say natural log of n is greater than e to the any positive number, which it could be. The reason I choose e is I want natural log. See, I want to get rid of the natural log. Okay. Yeah, you can also directly to see how can I want to prove that this is true, right? I believe that's possibly true. So how can you do that, right? Right? Yeah, then you put the natural log on both sides to see if I am able to square. So right, natural log of n, right? Okay. Then you will see that this natural log can be taken out, right? So you will get natural log of n times natural log of n greater than 2 natural log of n. So the above inequality is equivalent to this inequality. Okay, natural log. So I think this is a possible, right? Because when n getting larger and larger, and clearly this number is going to be greater than or equal to. So I guarantee the question is what is the smallest number, n here, right? The smallest of n, and then you put the e there, right? Yeah, then you solve for n, okay? Then you can get a number n, right? So natural log n should be greater than e squared, then n should be greater than e to the e squared. So again, you come back to that number. Okay, so the above inequality holds when n is greater than e to the e squared. So in other words, for n greater than e to the e squared. Okay, so this is what we got here. At the beginning I just guessed, I just guessed. I wish to show that this is greater than n squared. And I simplify, then oh, that is equivalent to n greater than or equal to e to the e squared. That's possible because when n is sufficient large, this is always true. So that's why, yeah, that's why we have this. I can guarantee this in court. Yeah, this is what I want. Yeah. Okay, those two are equivalent in equalities. Okay. All right. Great. My next problem is this. Okay. I make a similar version. First of all, the nth root, this is nth root of 2. This limit is going to be 1. 2 to the 1 of n, that's going to be 2 to the 0, which is 1. Okay, so this nth term approaches 0. How fast it approaches 0? I don't know yet, right? Then, is this going to be convergent? Right? This is going to be greater than 0. Okay, so please think about this. I have to prove it. All right. Okay, now it's possible it's divergent, or it's possible it's convergent. Okay. You have to figure out what Bn you have to compare with, right? Okay, and try. Okay, so this is my n, right? So what is Bn? I cannot use a ratio test. I cannot use a Rota test here. I have to find the Bn to compare with. Okay. My guess is 1 of n. Okay. Let's try. Okay. And n over Bn is going to be here's 2 to the 1 over n, right? Minus 1 has 1 over n. So we have to find the limit of this. To find the limit of this, I needed to find the limit of this, right? As long as, yeah. So let's see. When x approaches 0, the numerator approaches 0, denominator approaches 0, so I can apply the Rupee test rule. So the numerator is 2x natural log of 2, and here's 1. So the limit is natural log of 2. So natural log of 2 is a positive number, right? This is a finite positive number. So that means n, the convergence of n, sigma n is equivalent to the convergence of sigma bn. But we know that this is a divergent. It's divergent, okay? Okay, so that implies this is divergent too. Okay, it is divergent by the limit comparison test. Right? Since this limit, natural log of 2 today, this is a limit is a natural log of 2. So they are, an is almost proportional to bn. Think about this, right? So that's why if sigma bn convergent, then sigma n convergent. All right, let's see if we can find another problem. Go to section 11.7. Wow, I did the most of even number problems. Yeah, let's see. Yeah, I like the problem, this one. I modified it n to the nth power. Actually, if I change to 2, it's already good enough. Okay. All right, so this one, it is going to be, the reason it's convergent is because I know that this is almost equal to a constant natural log of 2 to the n, right? So because of comparison, right? So this square is almost equal to n square natural log of 2 square. And this series is convergent, right? Right. So this is my Bn. Right? This is my n. And you can verify, the limit, okay? N over Bn. And that is going to be, n is going to be nth root, right? And divided by, divide by natural log of 2 square and 1 over n square, right? So the limit is going to be 1. Right, the limit is going to be 1. Let's put natural log 2 square here, and here's nth root of 2 minus 1 over n squared. Okay. All right, so this one, the limit is natural log of 2. right? We already did that. It's natural log of 2 is the limit. So square, which is 1. So it is being almost, we call it asymptotically, they're the same, proportional to each other, okay? So in this case, we know that this is a convergent. The reason is there is an n squared there in the denominator, right? Okay. Oops. Yeah, I'm going to do very fast. So it's convergent by the P-series test. So P-series is very popular. P-series test is very popular. Okay. So then it implies this series is convergent too by the limited comparison test. So you have to figure it out. It's not easy. Sometimes it's not easy to get the series you can compare with. Right? Mm-hmm. The series you're going to compare with. For example, this one, so n's 1 plus 100 of n. Wow. I'll let you to think about first. Okay. Okay. All right, so let's go back to this problem. We have to, it's not easy to see, right? It's anyway, this nth term is going to be convergent to 0, but does not guarantee this is going to be convergent, the series. There is a difference between sequence and series. Okay, and I can separate them. Okay. So the key point is this part. Okay. I remember right? N's to the 1 over n, this approaches 1. So if that is true, then n to the 100 of n approaches 1 to the 100. It's also 1, right? So that means that term is the denominator, does not play an essential role here in the convergence of the series. So now it's clear to me I can use E, which is 1 over n. Okay, so I'm going to take a look at the limit n over Bn. Here's going to be n times n to the 100 over n. Bn is 1 over n, so it's n over 1. And n canceled out. Okay. Okay. So the limit is 1. So the convergence of a sigma n and the convergence of sigma Bn, they're equivalent. But however, this series is divergent. Okay. This series is divergent because it's because by the P-series test, P is going to be 1, right? So it implies this series divergent. Okay. By the limited comparison test. You have to find the right one to compare with. You have to find the right one to compare with. Then how about this one? Here's n, natural log of n plus 1, and the cube. Right? I think it's convergent. Suppose there's no natural log of n. This will be 1 over n squared. Okay, almost like it, right? Now there is natural log of that, but this natural log is always less than or equal to, I don't know what. Yeah, you have to think about, right? So use a comparison test or use a Rota. You cannot use a Rota test. You cannot use a ratio test. You cannot. The instant test does not work here because it's n is convergent, clearly n convergent to 0. Okay. So it's better to use a comparison test to prove it is convergent or divergent. Okay, you think about for 1 minute. Can you find the Bn to compare with? All right, I hope you figured out. I guess this is convergent. How do I know that? Well, natural log n compared to n can be ignored. But right now, it looks like n over n cubed. Then it'll be simplified to n 1 over n squared. So that the corresponding series convergent. Okay. But if I use a Bn 1 over n squared, then still does not work. If I look at the limit, okay, look at the limit, that's a problem here, okay. If I look at the limit n over Bn, okay, this is n natural log n over n plus 1 cubed, and that will be 1 over n, so n squared over 1, right? All right, so what I got here would be n cubed natural log of n plus 1 cubed. So I divide numerator denominator by n, I'll get 1 plus 1 over n cubed. The limit is infinity over 1, it's infinity. So that means sigma, yeah, that's infinite. So be very careful. So this convert, they're not equivalent. Now, is this Bn is convergent? That's true. This Bn is convergent by the P series test. But this does not guarantee this is a convergent. Okay. The reason is this limit must be finite. Now, actually, what you got here is that Bn is greater than less than equal to n for large n. So the term on the left-hand side is finite. Does not imply the term on the right side finite. This finite does not imply the one on the right-hand side is finite. The one on the right-hand side may be still positive, as this does not imply the finite here, okay, of this one, right? Because in core the directions less than equal to. So a finite number can be less than equal to an infinity number. It's the wrong choice for Bn. That's why I say it's difficult to choose the right Bn. Well, I can, how about that? I can let Bn to be not n 1 over n squared. Then I just need a half of the Bn, 1.5. That's probably good enough. This one's still finite, right? Because P is P is going to be 3 over 2. Right, it's greater than 1. But then this is good enough. This decays a little bit slow. So in this case, the limit that is going to be, we are going to have a limit, okay? Right, I can still write it in the form, let's simplify, right? This still n, for example, n squared, but I can put the square root of here, right? Then after you simplify it, you will get, and that is going to be natural log n, n to the 1/2. Okay. So now, yeah, after you simplify, so the first one, the limit is 1. The second one, the limit is going to be 0. Okay, by looking at this rule, it's going to be 0. So the answer is the limit is 0. Then 0 is okay. 0 is okay. Okay, the limit of n over n is less than 1. So that means if Bn is convergent, then n sigma. Okay, so Bn is convergent implies this will be convergent. Okay, that is okay. Okay, by the limited compression test. Okay, there's a one, the limit is less than 1. Okay, it can be 0. The reason is, here's a key idea, because the limit is 0, so it's less than or equal to 1/2 for larger n, right? Therefore, this is less than or equal to 1/2 for larger n. Therefore, you have this encoded, right? So the series on the right-hand side is finite, implies the series on the left-hand side is finite. Okay, so that is the idea, key idea. All right. Here, I'm not going to that. So we did enough exercise.